Hello, everyone. Welcome back to Primitive Computing, and looking forward to doing another night of some coding. And thanks everyone for who watched the last episode and the comments and likes and all of that stuff. So tonight, I want to pick up where we left off before. I had originally thought about making some kind of changing directions and getting into doing some trying to build a programming language from scratch, but I don't know. I felt kind of defeated that I left with what should have been a really simple bug to fix last time. Just kind of got stumped by that. Um, if you remember, that was not being able to display text on the screen. So the first, I figured out the bug for that, and the first thing I want to do tonight is to go and fix that. And then, there's a lot of the code that we wrote last week, or that I wrote, was really pretty bad. And so I'd like to sort of start building some better practices, and so we're gonna go just kind of clean up the code and make it look better, and that'll give us a good foundation for what we want to build after this. And then who knows, maybe we can add some extra features, we can add some color, we can add keeping score, or who knows, we'll see. There's only so much code you can fit in 512 bytes, so we'll see what we end up with. So I've got QEMU running right here. Let me if I can remember the key. Okay, let me zoom in a bit. So if you remember, like the way we play, we've got, it's a little bit choppy. I guess choppy when I'm streaming, but we've got the ball bouncing around, and then you can use the keys to move the paddle. So we can move the left paddle, or the right paddle, I mean. And keeps going. And so I'm playing both paddles by myself right now. I could get a friend and we could try and do this together or whatever, playing against each other. Although the thing is, if I hold down both keys to move both paddles at once, then only one moves, so that wouldn't be very good for two-player. But yeah. So you notice there was one of the bugs there is you can actually move the paddle down. I don't think it will block the ball if I move it down too far. Nope. That one's invisible, but so there's no bounce checking on paddle movement just yet. So that's something we can add tonight as well. But let's start with the bug that I didn't fix last time. So if I wait until we score a point, then we switch into text mode. And if you remember, we were supposed to see a message on the screen that said we were supposed to see a message that said that the player scored a point, and then it says press any key to continue, and then we can continue on that way. But instead we get a blank screen, so we need to fix that to start with. Just a sec. Let me. It says my stream is not real healthy right now, but hopefully it'll pick up. So let me. We'll just plow on ahead here and see what we end up with. So sorry about that. Anyway, so I'm going to exit out of QEMU, and so here's our code before from the night before, the last night. I added, when I posted up to GitHub, I added this open source header up there. So, that's not very large. Let me make it bigger again. Yeah, that seems readable. Okay, let me make the terminal a bit smaller. Okay, you can actually just get rid of the terminal for now. There you go, cool. So anyway, as I was saying, I added a license header on this, so all the code that I'm writing tonight is going to be released under the Apache license, which is a pretty liberal open source license, so you can do whatever you want with this. So please feel free to study the code, improve it, or whatever. If you do make changes, let me know, because I'm curious to see what people do with it. Anyway, so we walk through this, we sort of clear out some, set up some registers and all that. We set the video mode, we get set up so we can draw in there, and then we draw the box. So we draw the line across the top, draw the line across the bottom, and then we draw the sides. And if you remember, I kind of cheated there and wrote, what I actually do is I draw one line that's 2 pixels wide, but I draw it on the very rightmost edge of the screen. And then because of wraparound, we end up drawing a line on either side of the screen. So that was, I don't know, saved us 4 or 5 instructions basically by not having to draw both lines. Actually, I don't know. It may not actually be shorter. That might be a fun thing to play around with. Because this sequence here to draw a line is only like 3 instructions, and maybe the loop is more. So who knows? Anyway, then we go into our main loop. So every time we go through this, we draw the paddles, and we draw paddle 1, draw paddle 2. This is something that I think we could really factor this out into a subroutine, and so maybe that's a good option to do this. And that way we don't have to just duplicate the code. That also means that if there's bugs in this, then we don't have to fix the bug twice or remember to fix it twice. There's just, when you copy and paste code, it's really easy for stuff to go wrong. So it's not great there. So then we draw the ball, which is pretty simple. We compute the location, like the memory address for that pixel, and then we write the size, we write the color. So we use bright white, which is 15. We write that into the screen or into the video memory, and that draws the ball. And then we do like the game logic. So the first thing we do is we make sure the ball is in bounds. So we check against the left wall. If the ball hits the left wall, then we say the player 2, so the player on the right scores a point. And if we, excuse me, and so we check the top and bottom rows, I think that's checking the paddles. This is why we should comment our code better than I've been doing. But anyway, we'll try and clean that up a bit tonight. So we check I guess that's what we're doing, is checking to see here whether the ball has hit the left paddle. We check if it's hit the right paddle. And then, check Y bounds. That's probably, top and bottom. So that's checking the ball hitting across the top and the bottom. So then we check for keystrokes. So here I'm just using the bias key options, and I think that's part of why we can't have 2 concurrent keys at the same time. We're not checking for like key down and key up. We're just anytime there's a keystroke, then that's what we listen. So like you don't want to just hold it down. You have to like tap 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 tap. Yeah. Anyway, this is one of the things I'd like to fix too. So we just added delay loop into the game because when people wrote code like this in the first place, they were probably running even back then. Their computers were fast enough that you could probably run this faster than players could keep up with. So you have to slow things down. This is just a loop that counts really high, and in doing that takes time, and that sort of slows things down. But it's also kind of, I don't know, maybe 30 years ago this was a okay way to do it, but like it doesn't work that well as your processor changes, and it also puts a lot of load on your system, uses a lot of energy and stuff like that. So if we can get rid of this and use like timer interrupts, that would be a better option. And then we sort of get ready for the next iteration. So we erase the ball, and then we calculate its new position, and then so down here is we go back up to the main loop. So that's our jump back up to the top. So we just repeat this over and over and over. And then we have this other section down here, which is the part that was broken, where we want to display these messages to say, hey, the player scored, player 1 scores, or player 2 scores. And then, so we draw a string in there. And this is the part we were having trouble with before. Okay. This is, again, something that could have been a lot more cleaned up, but, I was rushing to get code done really quick. So I didn't do it the cleanest way. So, it's a string loop and string loop 2 are basically the same function, and that's because they are like I literally copied and pasted them and made some changes to the labels and stuff on there. So this is a prime candidate to refactor into another function. And then we just wait for any keystroke. So one of the things we print out is press any key to continue. There we go. Press any key to continue. Here's a couple of memory locations to store all of the game state, basically, so we can load and write to memory. It might be possible to fit this all in registers. I think if we were running in, actually, we could use the 32-bit registers to do this. Or if we were running in like long mode, we could probably, 64-bit mode has a lot more registers available. So we could probably keep the whole game state in registers. But it's not too hard to stick it in memory either. So, and then this section down here is just saying, so we're using raw assembly mode where NASM, our assembler, just writes out a sequence of instructions. This is sort of separates it out into another, excuse me, another section, and then all this is, there's a signature that the BIOS looks for at the end of your boot sector to say whether it's bootable or not. So basically, it looks at the last 2 bytes of the sector to make sure it's either that it has this string here of 0x55, 0xAA. That's how the BIOS knows that this is a bootable disk, or at least a bootable disk image. Okay. This also has a, so if I go back into my terminal, this also has this like nice effect of making our boot sector that we're building exactly 512 bytes. But the downside is it also hides how close we are getting to the limit. So to show what I mean there, this is something I figured out while I was figuring out how to fix the text bug. We're actually running really close to the 512 byte limit. So if I run NASM here and then I look at the size again, the code was 509 bytes. So last week that was where we ended, is at 509 bytes. The boot sector itself is 512, and the last 2 bits are taken up by, or 2 bytes, I mean, are taken up by this boot sector signature. So really we had 510 bytes to work with, and I came in right at 509. So I had 1 byte to spare when this is all done. So that's gonna lead to some sort of issues, I guess, that we need to deal with. So I will uncomment this, and we can start fixing the problem with the text. Okay. Scrolling back up here to where we draw the display. I mentioned that this was going to be really simple, and it turns out it was. If you look at these instructions right here, I'm loading the address of the text mode memory. So I'm sure there's a good reason for this, but I don't offhand know what it is. But the VGA device has its video RAM, basically the memory where what's displayed on the screen is shown. It's like mapped into memory, and but for some reason text mode memory is in one location, and then the video mode or graphical mode memory is in another location. So what this is doing right here is it's loading up a different segment register to make it easy for us to interact with the text mode memory rather than the graphics memory that we've been looking at. Okay. Anyway, so the mistake I made is so you can't load into segment registers directly, at least as far as I know. So what you do instead is you load the segment you want into a scratch register like AX here. And then you want to move AX into the segment register that you are looking for. But the mistake I made here was that I got this backwards. So what I was doing is reading the ES register into AX, and I should have been storing the AX register into ES. So the first thing I need to do is I need to switch the order of those arguments. Okay. In theory, this would fix it, but it turns out there was another bug that I made. So let me show you. There goes, it's running. Ball goes, we wait for it to hit the wall, and we still get nothing on the screen, right? That's the problem we've been having, basically. So what do we do about this? I made another mistake, and let's see. Here it is. This JZ instruction here. That actually is supposed to be, well, so what I was trying to do is the strings that I put in here are, you notice they have this 0 at the end. This is how you build in assembly language a null terminated string. So I just have a bunch of bytes. It's a bunch of ASCII characters here, and then a special 0 byte at the end of it. And so this is if you've written C code, which I assume you probably have if you're watching an assembly language live stream. C uses null terminated strings, where it's just a sequence of bytes with a 1 0 byte at the end of it, and that's how you know the string is over, or is at the end of it. So the goal here was to load the next character in the string into the AL register, and then you do JZ. So if the last thing we did was 0, then exit the loop. Okay. It turns out there's a couple of problems here. So one, I slipped in this extra instruction here. So what I would actually be, in theory, what this would be doing is saying, oh, if 15 is 0, then go to the exit loop, otherwise continue. So when I saw that, I was like, oh, this should be an infinite loop, and it wasn't, or it should, walk off the end and start reading garbage memory, or who knows? Like bad things happen when you don't like exit your loops properly. So anyway, it turns out the problem is that the move instruction does not update the flags. So the CPU has got a set of flags for different conditions. Whether something was 0, whether it was like less than, or like I guess it's a carry flag that it uses. So it has these flags that then it uses to figure out whether like a number was less than or equal to, or this is how you do your conditional jumps. So we actually need to check and make sure what the we need to make sure what the value, we need to actually explicitly test the value that we just read. So the first thing I'm going to do is, this was just changing the color of the register. I'm not actually going to bother doing that. Instead, what I'm going to do is just go back to moving AL into memory here. This is actually what I did done in string loop 2. So what I'd been doing is trying to change the color. I was like, oh, maybe we didn't have an explicit color set, and that's the problem with it. So I'm going to get rid of that. But then the thing we need to do is we need to explicitly test the value of AL. So we're going to test AL against AL. That compares AL to itself, and then if it is 0, then it sets the 0 flag. So then the JZ instruction will jump if 0. So I think we have the same number of instructions, so hopefully we'll stay within that size. So we did. And if I run this again, we should see a message going. So let's see. Yeah, so it says player 2 scores. Hooray! Good. Fix that. Actually, I think it said player 1 scored, but I said player 2. Yeah, player 1 scores. Great. But we have this problem again, which is where the next this pressing the key to continue did not display on there. And this is the same problem again, so I forgot a test instruction here. So let's add test AL. And if I run this, okay. I'm glad that this happened. I'm glad NASM didn't just decide like, oh, I'll just like overwrite one segment with the other or something like that. But our code has now, we've gotten above our size limit, and so we've overlapped in this boot signature section. So I'm glad we have this hard warning there to say, hey, you've used up too much space. So now we've got to start saving some code. So I'm going to do the easiest thing I can think of, which is to make the game a little bit less exciting and take out these exclamation marks. I guess I could just get rid of the press any key to continue, but that's kind of sad to do that. So let's not do that. Let's compile it, or assemble it, I guess. That's what you call it when you're doing assembler. And run this again. Let me see if I can make that bigger. Yeah, there we go. Okay, so now we have player 1 scores, press any key to continue. Great. Whoops. Oh, I missed. Oops. Okay. Sorry, this probably isn't super exciting watching me play, black and white Pong on my screen here, but it is what it is, I guess. Cool. So there we go. Player 1 scores. Press any key to continue. I do want to prove that player 2 is also able to score. So let's see if I can move this to make that happen. Last time I did it, but I pressed the key too fast and we didn't see the win happen. Whoops, that still didn't show anything. Let me try again. There you go. Player 2 scores. Perfect. Great. We got that. Okay. Oops. We can exit out of this now. So we're done playing. And let me go ahead and let me commit this. So we fixed the fixed text display bug. I did actually go ahead and upload basically that exact patch to GitHub, but then I reverted it so that I could show the process of going through this again. Okay. Okay. Let's try and do some function calls now. So let's say we have this like drawstring and string loop and all this stuff. Let's see if we can factor this into a single function that we can use. Okay. And then we can just call it twice, and maybe that will save us some more space. So let's see how we're doing on space, first of all. So I'll use my little trick of commenting out this last section. ls. Okay, so we're still at 509 bytes. So we've got one extra byte to play with. So we're cutting it really close. So we may not be able to do any extra functionality because we're going to be stuck with just the these extra bytes basically. So so if we look at what's in common with these two, they're all like the inputs to these two different loops. We use the SI register, so the source index register. We use this like ESDI register, or combination of that as our destination register. And that's really basically it. Okay. So we're going to rewrite this down here as a, let's go down a little bit. I don't know. Let's go down past the end of all of our code here. And so we're going to make a new function that we're going to call, I'll call it print string. Because that's basically what we're doing. And let me add a comment. So this is print string. And so if you're using like an actual like high level programming language, you would you have like a calling convention, and there's like a good sequence for how all of this goes. Since we're writing, or for all of this goes, what I mean by that is how you pass parameters, how you do return values, how you do like what registers you have to save before you call the function, what registers the function has to save before it can use, and so on. So we don't have a standard yet for how to do this. So instead, I'm just going to document really carefully how all of these things work. So we're going to say SI is the this will be the basically a pointer to the source string. DI will be a pointer to the destination location. And that's basically it. There's no return. There's no, so we'll say returns nothing. There we go. Okay. So we're not going to need any stack. We're not going to need like a frame or anything. We're just going to honestly like take exactly this code here and paste it down here. I'm just going to, rather than like call it exit loop 2, we're just going to have exit loop, and oops. And we're going to jump back to like I'll create a label called begin here. That's just in case we ever need to add a function prologue to this. We can add it in there, and the rest of the code won't change. So now, because this is a function, so you call it by saying call print string, and then when you get to the end of it, we want to return. So we can just call, or we just use the ret instruction. And now let's see if we can replace the code that we had just written here. So here, okay, so at this point, we set that up. We've got our DI set up. I think SI, yeah, we set up SI back up there. So we're just gonna replace this with a call to print string, and that should basically do it. So we don't need the string loop anymore. And then we want to do the press any key to continue. So we load our press any key, we set our destination. And then rather than doing this string loop 2 again, we call print string again. So let's delete this code and whoa, accidentally hit Control Tab. There we go. So we assemble it. It all fits. I want to actually see how many bytes we saved by doing that, because that'll tell us what we can do with other stuff. Hey, we're down to like 499 bytes. So that saved us 10 bytes by combining those two functions together. So that's pretty cool for us. But saving 10 bytes is no good if it doesn't work anymore. So let's run the QEMU here and see how we do. And oh yeah, I didn't reassemble it with the after I uncommented that last section there. So let's go. There we go. Hooray, it prints. We have player 1 scores, press any key to continue, press any key. Now let's go up. Let's see if we can make sure player 2 is able to score 2. Here we go. Cool. Now we gotta wait because the game is slow. And it's going. Bounces. I should do sound effects. It should be a bloop, 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 bloop. Yes. Oh, there goes. Player 2 scores. Man, that took longer to come up than I expected. I guess this is like what it would be like when I was running on like an original like IBM PC that had like a 5 megahertz processor. So, there you go. Cool. So that's working. Let's see if we can improve some other things in this. So I mentioned that there was. Okay. So this is weird having the having our strings like intermixed with code. So I'm gonna move this down. There we go. We'll just keep all of our strings and memory and stuff together down there. Let's see. If we want to try to save a few more bytes, there's another trick we can do. If you notice, these strings here are basically the same. So why don't we just keep them, And let's just do let's change this to like player X scores. I'm going to split this up into a couple of strings here. So that one we don't need a label on. We just do it like that. And this is just going to be score message. And this will be message player number. Okay. So what we're going to do is rather than like copying the string, we're just going to overwrite this X letter here with the number of the player that is playing. I guess that means we could also make this support 4 players if we wanted to. So what we do is we always are going to, let's see, we're always going to load this, but I'll move it down to drawstring. So move SI, and this is just going to be, I think we called it point message or something. Score message, that's what we called it. So with score message down there. But what we're going to do instead is do move into, I don't think you can just like do 2 immediates, but I'm going to try it, see if you can. Player, message player number, that's what we want. And we're going to move the character 1 in there. And then down here, we move the player or character, whatever, 2. So Nazm's going to complain, I think, to this. It didn't explain what I thought it would, though, so let's see. Oh, right, I forgot to do db to say we're making data. And then the size is not specified there, so... Oh, yeah. Maybe this is going to work, actually. Just to specify the size. It does work. I'm like genuinely surprised you can do 2 immediates like that. I guess this is that CISC versus RISC instruction set. Let's see now. So we were at 499 bytes before, and let's see how many bytes we're at now. Oh, we saved another 11 bytes, so we're down to 488. That's good because that gives us some more space to play with if we want to do other stuff. Let's run it and make sure it works. Oh, once again, I forgot to rebuild it. So Nazm, there we go. And QEMU. Okay, here we go. Player 1 scores, and let's make sure that player 2 can score now. Here we go. Bloop. And there goes, player 2 scored. So it looks like it's working. I'll do one more just to make sure that player 1 can score again, that we don't like overwrite it for good. But I think we're looking pretty good here. Yep, player 1 scores again. Great, that's what we needed. So there we go. Now, yep, we have less going on there. But we've saved some space there. We've saved some of our strings. I think, we can go ahead and put the exclamation mark back in there, and because I like having that, and we've got the space to do it now. So let's commit again. I like to commit really often. I didn't do this last time because I hadn't made the Git repo yet, but let's do that here. So we're saving a few bytes from duplicate strings. There we go. Cool. Okay. Let's continue. And one of the other things I pointed out that I wanted to fix was the busy waiting loop in here. Excuse me. Whoops. That's down further. Excuse me. Okay, so this is a busy waiting loop. There's a lot of problems with it. Like, one, we don't like it, it's sort of bad for the rest of the computer. If this were actually a boot sector, I'd be the only thing running on the computer, so it doesn't really matter if I'm playing nice with other processes running. But since I'm actually running in an emulator, it slows down the rest of my machine when I'm doing this. So that's kind of a problem. But I think the bigger problem is that the speed varies based on what else is going on the machine. So like I was playing this a little bit before I started my live stream, for example, and it was actually quite quick, almost sort of too fast to play. But then now my system's pretty heavily loaded with doing the stream, and so that's causing, that's causing it to be a lot more choppy and a lot slower. So let's see if we can maybe make this a little bit less, CPU intensive. So what I want to try is, I don't actually know if this is going to work. I'm just trying it out. But there's an instruction that the CPU has called halt, or HLT. And what this, at least what I believe it does is, my understanding of it anyway, is that it puts the CPU like to sleep, or it stops execution until an interrupt happens. So basically this is a way for the program to say, like, I've done everything I need to do, wake me up when some external event happens. And so that can be a couple of different things. Like that can be your keyboard, for example, is an interrupt. So if someone hits a key, then that's an interrupt. But the other thing is there's a timer interrupt, and I was doing some reading about this over the past week, and the timer interrupt. I was afraid I was going to have to program it myself and set it for the time that I want and everything, and but it looks like the BIOS actually sets a timer interrupt running just for its own purposes for whatever reason. And I believe it's set just under 30 frames a second. So, or 30 times a second, 30 hertz. It's like 28.88 something or other. So we do have this periodic interrupt that's already set up, that's already running. So I think this halt instruction should be a way for us to not have to do so much, but also go to sleep and then wake up periodically. And then as long as we can do all of our game logic, which in less than a 30th of a second, which it's less than 512 bytes of code, like we should be able to do that. Then this should also have the side effect of fixing this to run at a pretty consistent frame rate. So that's the theory. It should work. I haven't tried this before, so I don't know if it will or not, but let's try it out and let's see. So it's moving. Oh, that's funny. It actually goes faster when I type on the keyboard, because that means more interrupts are coming. So yeah, I probably need to actually check the timestamp. Yeah, I think this looks better. I don't know what everyone else thinks, but I think it looks better. Yeah, it's kind of hard to tell if it's more stable frame rate or not, but I think it's a little bit better. So I think I'm gonna keep this change. This looks good to me. Okay, cool. So that looks good. Let's just go ahead and delete all this code. We can actually improve it even more. First, since I'm like code golfing here, I want to see how many bytes we're at for compiled code. 474. What were we at? Like 488 before. So that's another 14 bytes, 15 bytes, I guess, because I added the exclamation mark. So cool. It's saving us some space. Let's rebuild that just in case I don't mess up again. And can't boot it up. But we can actually do even better here. So I mentioned there's this timer interrupt. Let me, whoops, I don't want task manager. I want my Firefox here. So we have the OS Dev Wiki that we looked at before. I mentioned the BIOS keeps its own timer interrupt for its own purposes. It turns out it actually has a counter somewhere in memory that it's always incrementing with like the timestamp on it. So we can check and see whether the timestamp has changed or not. And then that lets us tell whether it's a keyboard interrupt or a timer interrupt or whatever. So that will make it so the game doesn't speed up when you're playing or like when you're pushing keys. Okay. So let me. I was reading this instruction or this page pretty recently about this. I think it's like the BIOS memory map. Maybe if I just read about BIOS here. Common functions, hardware detection, detecting memory, BIOS in protected mode. Let's see. My dog just got up. He's roaming around a little bit, so you may hear him kind of scooting around. But yeah. He's done. He's laying down again. Just wanted to rearrange, reconfigure himself, whatever. Find a more comfortable position. That's not what I'm looking for. I'm looking for the memory map. So let me just search for memory map. Yeah, this is what I wanted. This is actually going to be useful for when we start actually using more memory than we currently have. We can, this tells us what sections of memory we're allowed to use. So this, I'm pretty sure the timer information is stored in the BIOS data area. Well, this says it's unusable in real mode. So I don't know. Well, maybe they mean you can't write to it. Yeah, here we go. The BIOS data area is that, so it's, these offsets in memory that have a bunch of some kind of just like useful information, like the display mode, the number of columns in text mode, video, number of hard drives. But one of these should be the timestamp. Let's see, number of kilobytes before. It might be in the extended area. Nope. I'm gonna search for time. Oh, here we go. This is the one. So this number of IRQ 0 ticks, timer ticks since boot. Okay. So I think this is going to be relative to a different segment because this BIOS data area is at the very beginning of memory, and so far everything we've been looking at is kind of higher up in it. So I think I'm going to do this all relative to segment 0. That seems like the best option. Actually, we could probably do it relative to segment. I always forget how the segment numbers work in real mode. It's like I think it's like segment 4, but let's just use segment 0 because that's more straightforward. So we have our code segment, our data segment, our extra segment. I want to keep another segment around. So let's you know what? I don't think we actually need those instructions. Let me try it without those instructions and make sure see whether this works. Here we go. Oh yeah, I was gonna make sure that like, you can actually score. That was like, why did I start this? Why am I playing this? So let's see. I think if the memory were messed up, we would have noticed something by now. But it doesn't hurt to make sure, Go, go, go. I think it is slowing down. That's really kind of annoying. There it goes. Now we gotta wait till we change video modes. We get player 2 scores. So that's what it should have said. So great. Cool. Instead, so we have these extra segments, at least pretty sure we do. I forget whether they're available in real mode or not, but there's also like GS and FS and so on. So let's use FS. So we'll move into AX, or we'll XOR it because that's better. And then we'll move into FS AX. I'm not making the same mistake this time. And so then we go down to where our loop is. And oh yeah. So we want to load the timestamp. The timestamp is so it says that the word's at 16 bytes, or sorry, not bytes, bits. So 2 bytes. So we'll just say we'll move into AX from FS, and we want 0x046C for 6C. Like that. Okay, so that's our timestamp. Then we're gonna we'll have our delay loop again. So what we're gonna do is we read the timestamp at the beginning. We're going to then halt, read the timestamp again, and if they are different by basically if they're still equal, then we know we haven't waited enough time, and so we're gonna we'll keep going. Okay. So we halt, and then we want to load into a different register. So we've got our BX register that we can use instead, and then we'll do we'll test AX and BX, and then if they're equal, we go back up the delay loop, and so we build. Great, it compiled, or assembled, so that means it's good, hopefully. And boot up. Okay, and it is not getting, well, I don't know if you can tell really, it's choppy still, but it does not appear to be getting faster as I'm holding down a key. So that seems much better. Cool. Yeah, so that seems good. And okay, I'll give it one more. We'll let player one score this next point, and then we'll continue on. Okay, there we go. Player one score is great. Let's exit out of QEMU. We'll commit again. So this is an improved delay loop. Okay, so now we're hopefully using less power. We're hopefully not burning 100% CPU. We're just, life should be much better now with this way of doing it. So great. So let's see, a couple more things we can do. Let's for moving the paddle, if you noticed well here I'll show again just real quickly. If you notice, like, we don't have really any bounce checking, so I can move the right paddle like all the way down, and then it comes up on the top like that. I can keep going up, and I'm not gonna make it in time. Oh, I did. But if I keep going up, then I come over like that. So that doesn't look good. Let's see if we can add some bounce checking to moving the paddles as well. And this is probably something that we should factor. Actually, first I'm going to refactor the paddle logic, I think, because it's a lot of duplicated code there. So I think that's a good spot for a function. Okay. That's hard to tell what we want to do here. Okay. Yeah, we want a new function. I think that's that's the best way to do this. Yeah. Sorry, I should be thinking out loud more than what I'm doing. But anyway, so I'm trying to think for. Well, okay, let's start with a comment. So let's do. Um, you know what? No, I'm not going to do this because this isn't actually, this is a different section. So this was about refactoring the bounce or the ball, checking the like whether it's hitting the paddle or not. This would be a great place to refactor this because this is probably half the code in the game. So we could clean it up and save us a lot of code there. But let's instead look at this moving the paddle part here. Let's see. So this we could actually probably refactor if we wanted to, but it's not too bad. Let's see. So here's what, yeah, we're just gonna add a quick little guard on here. So this is where we move the paddle up or down. So okay, I'm gonna make a function for this. So we're gonna have it's called move paddle up. And so let's see. Let me start out with just a comment for it. So our inputs are going to be, let's stick in, I don't think we're using AX. Yeah, we can use AX. So AX is going to be the address of the paddle position. And then yeah, that's going to be it basically. I think that's all we need for it. Okay. So to do what we did before, this is, so we're going to have move paddle up, and then we subtract and we return, and this is just going to be AX. So we can call it now. So we can say move AX P1 pause, and then we call move paddle up. And this is basically like, I'm pretty sure this is going to use more space, but it means that like we won't have to duplicate all of the rest of the code that we write on here. Okay, so it should be an improvement overall. So here we're going to move into AX P2 pause, and then we call move paddle up. Okay. So for moving paddle up, we've got that. Let's do this for down too. Let's just go ahead and get it done. Oh, that's not red. Return, that's red. And the only difference here is it's add, because increasing Y goes down, not up. Okay. I'm going to move all this down to the bottom with our functions just to make sure that I don't, mess up the control flow around this. So we go down. Here's our print string function. Here's going to be our other functions. And then so okay, we have move paddle up, move paddle down. Here I am copying and pasting again. Move paddle down. I could probably factor this even, or like refactor this even more, but that just seems kind of like, I don't know. I think in that point it's going to have so many arguments that I'm going to end up duplicating code and just calling the function. So that's why I'm doing it this way instead. It's better to have just a small function At least that's, I don't know, it may not be, but that's kind of my logic for right now. Okay, so we have move paddle up, move paddle down. Let's make sure we can still compile and run this. Whoops, invalid effective address. Was it 263? Oh, okay, here we go. So this is where, I don't know. I don't know what's wrong with this. Maybe if I do it relative to DS. Nope. I bet DI works. Let's try that. Cool. Okay, so that means instead of AX here, we're using DI. And that means up here where we call it, we need to change our AX into DI instead. And that's going to be a problem. Okay, because we have DI, we just saved DI from the ball up here. Where is it? I don't know, wherever it is that we draw the ball. Oh yeah, there it is. Oh yeah, okay. So that's where we draw the ball. Let's go ahead and, so I'm gonna use the stack now and we're gonna push DI and save that because we're gonna need to overwrite DI later. Okay, so now we're able to use DI again in the when I'm calling these. Okay. And then at the end, here we need the pop DI. All right. Cool. And hopefully this still runs. Yeah, this gets like slower and slower as the night goes on. There we go. It seems like it's working though. The paddles. So yeah, the player scored. Oh, I seem to have messed up again. The K is supposed to move the right paddle down, but it doesn't. It moves the left paddle down. So I bet that was a copy and paste error. Let's go find. Yep, that's supposed to be P2 pause down there. So we rebuild it. Okay, now I can move the paddle all the different directions. Great, that's working. Okay, so now that we've got this refactored, rather than having to like write the comparison logic twice and copy and paste it for each paddle, I can just write it once here in this function. So let's see, what we want to do is basically skip this if we are over if we're out of bounds. So we're moving the paddle up. We want to, so let's okay, let's push AX because we want to be a good function and not mess anything up. So we'll move AX or move into AX the position DI. And then we'll do compare AX and 1. I think we can just do it as an immediate like that. And then we'll have exit here as a loop. So if we're equal to 1, then we can't go up anymore. So we will do JE exit. And then we're gonna have to do the same thing. Well, not exactly the same thing, but a similar thing there. So we need our exit label. And this time, instead of comparing against 1, we're going to compare against 199. So our bottom edge of the screen. So hopefully this is all. Oh no, we're out of space again. Let's see by how much. Okay, so we do ls primitive computing 516. So we need to save ourselves 6 bytes somehow. Let's see what we can do about this. Well, we could refactor all that logic up above, but that's more than I really feel like doing. Hey, this looks like this is probably 6 bytes here. So there you go. Press any key. Okay, 504. So we've got some space to play with again, but let's see if this works. Oh, NASM. We're at 512 again. That's good. It means we have our boot sector signature on it. And runs. Let's go increase the size of this. Here we go. So let's see. We should not be able to get up above or down below the screen. Let's try that. Oh, that did not do it. Ooh. I think I have frozen up my game. So we got an infinite loop in there. That's fun. It always happens like right when I'm like, oh, okay, I've almost got enough stuff done. Let's just call it a night, you know? And then I get one of these like silly bugs in there. So, yep, that should be okay. Okay. Oh, you know what it was? We did not pop AX, and then down here we need to pop AX also. So I think what happened is we ran over the end of we overflowed the stack, and then that was the end of that. Hopefully we have enough bytes left for that. I think we do. Okay, so we're gonna go down. Well, that seems to have happened even faster. Oh, and that's because I didn't push AX there. Well, yeah, that'll do it then. We will underflow the stack very quickly. Okay. Yeah, so moving now. The game hasn't locked up. But we keep going off the end. Okay, so we're gonna keep going up here. I don't think I'm gonna be fast enough to make it in time. There we go. All right, I think yeah, so we can't so we've got the bottom bounds. Oh, you know what the problem was? This will happen over here as well. So over here we can't go over the top. But we are stuck in how low we can go. What I forgot to do is take into account the width of the paddle. So we don't actually want to compare against 199 here. We want to compare against the 199 minus the paddle size, which was 25. So let's see, 199 is the bottom row, and 25 is the paddle size. Okay, so let's build this again, run it. And then here we go. So, oh, keep going down, down, down. Yeah, the player scores. Let's see, can I? Maybe the paddle size isn't 25. Maybe it's 50 because it does stop me. It just stops me in the wrong spot. This would be a great place for like a constant, but I still haven't, I guess, graduated to that level of clean code yet. So here we go. Let's run this again and see what we get. Okay, zoom in a bit. Yeah, let's go down. Sometime I'm gonna have to figure out how to make the timer interrupt faster. I don't know if that breaks the BIOS or not. Like, I don't know how much it assumes that like the timer is set at a certain time, but great, we are stopped. If you notice the that little blank spot that happens in there, that was because of another cheat we made before, where instead of having to deal with erasing the paddle or not, we would just go and we just drew a black spot on either side of the where the paddle was, but I don't think I feel like fixing that right now. Okay, let me make sure the top bound is still in place. Yep, it is. Great. And then we'll keep going down. You know, I think the real test of this halt instruction that I did will be once I stop my stream tonight, see if the game still runs at the same speed. Because in theory it will. That's what it's supposed to do. Okay, I don't wanna have to restart just yet. But here we go. Okay, the left paddle stops at the bottom. And now we're gonna keep going up. So you can't see what keys I'm typing, and it's probably something I should change, is make it so you can actually see my keystrokes. But here we go. That's maybe, I don't know, I'm always trying to improve my stream, always trying to improve my you know, my presentation and stuff. So that's maybe something I can do. And if you're watching this and you have ideas for things that would make this more engaging or more interesting or whatever, let me know, and I'll see what I can do. Oh, okay, we made it. And then player one's gonna score. Okay, great. There we go. So that gives me the bounce checks, and I think we're getting close to a pretty good spot to wrap up here. What I'm gonna do, I think I've teased this a couple of times doing color, and I would kind of like to add some more color to the screen. So I'm just gonna, I was gonna do some custom colors in the palette and stuff, but I think instead let's just do some of the colors that we have to start with. So let's do, let's see, mode 13H default palette. I never know how to spell palette, like how many L's and T's. I think that's it. Not my search engine will help me out here. Yeah, here we go. Well, there's the palette. Let's I don't know, I'll just use a couple of these colors. Let's use maybe yellow for the borders, and then green for the whatever, the paddles and the ball. So let's see, yellow should be number 14, and then let's see, 13, 12, 11, 10. So 10 will be the, so we have 14 and 10 are the colors that we want. So when we're drawing the box, let's do, instead of 15, we'll do 14. And we use that for the bottom line, and for the sides, we need 0xEE, so 14, 14. And then to draw the paddles, we're going to use okay. Okay. And then for the paddles, instead of using 15 again, we're going to use 10 is what we were doing. So that's paddle 1, and then paddle 2. Yeah, this would have been a great thing to collapse into a single function. But oh well. So now it should look a little bit prettier. Yeah, there we go. So one thing about this too is it's just kind of, oh, I left the ball as white, but that's okay. Well, I think this looks a little better. It's nice having some color. It's nice not just being a black and white screen. So there we go. Cool. So that I think was all I really wanted to get through tonight. There's always more I think we could do on this. There's a lot more code golf that we could do. There's a lot more functionality we could try to squeeze into that. There's still no score keeping. There's still uh, doesn't show anything like on the screen. It'd be nice if kind of along the top here it showed the two players score, or we had more instructions or whatever. But I think this is probably about the. This seems like a pretty good spot, and I'd really like to start moving on to trying to build a more complete operating system or more like usable system rather than just playing around in the boot sector. Um, so anyway, that's this. I think be as good a place as any to wrap up. I think next time I'm probably, since we're running right into the end of the 512 bytes of that we have available to us for in the boot sector, or 510 bytes, I guess. I will probably the next place to start is reading from disk and loading up more code into memory, and then maybe once we have that, I'll see if I can get we can start building a higher level programming language too, so that we don't have to do everything in assembly, and then maybe start working towards a self-hosting computer system, so we can start